Alright, so we're getting into the last section of chapter 6. This is 6.5. This is split up into two videos. We'll call this one day 1, the other one will be day 2. Neither one of them is all that difficult. So we'll go ahead. This part right here is primarily some algebra, an algebraic way of breaking down what's called partial fraction decomposition. And you've seen this in pre-cal, but we're going to cover it a little differently. And the whole purpose for this is that if you have the integral of some quotient, where the top is a polynomial and the bottom is a polynomial, then you can actually use partial fractions to break it up into the sum or difference of two much simpler integrals. And that's what partial fractions are used for. All right, so for instance here, we've got the integral of 5x minus 3 over x squared plus 2x minus 3 dx. Now, it's not real easy. You could use u substitution and have down here, have u be x squared minus 2x minus 3. There's only one problem with that. There's no constant multiple that you can take the derivative of this and make it into that. So that's where our partial fraction decomposition is going to come in. What we're going to do is we're going to write it as two separate terms instead of just one. First thing you're going to do is you're going to factor the denominator. If the denominator is not factorable, then you're kind of stuck with dealing with that as it is. But if it's factorable, you're going to take it, you're going to factor the denominator, and what you're going to do is you're going to rewrite this as the sum of two fractions. One fraction will have the denominator that is the first fraction, or the first factor here, and the other one will have the denominator that's the second factor here. And it doesn't matter what order these in. A and B are going to be in the A, whatever you find for A with this problem will always end up over the x minus 3. So if this had been B, it's still going to end up being the exact same number. So don't worry so much about which one's first and which one's second, because it doesn't matter. And what you're going to end up doing, and there's two ways you can think about this. The first way you can think about this is you're actually going to multiply all the way through the top by the common denominator of these two. Well, actually, you're going to multiply everything through by the common denominator. So and I'm going to show you how this works, and there's two ways of thinking. We'll talk about both of them. The first way is if you multiply this whole thing, by the common denominator of x minus 3 times x plus 1. Now, when you do that, if you multiply this thing, you've got to distribute it to the two different parts here. And if you multiply x minus 3 times x plus 1 times a over x minus 3, you're going to end up with a times x plus 1. And if you multiply x minus 3 times x plus 1 times b over x plus 1, the x plus 1s would cancel out, and you'd end up with b times x minus 3. So with that, you could actually go through and solve. And all you're worried about is the numerator. This right here is what the numerator, how the numerator would come to be if you were to combine these two things together. Now, the reason this works is because if you had to multiply this one times whatever would make it a common denominator where you could put these two together, you'd multiply times x plus 1 over x plus 1. That would give you the x minus 3 times x plus 1 on the denominator. And then you could combine it with this one over here when you multiply it by x minus 3 over x minus 3. That's the other way that you can actually do this. You can think about this thing as being able to add these two together. So you would end up adding this first one by x plus 1 over x plus 1. And the second one over here by x minus 3 times x minus 3. So what you end up with is a times x plus 1 plus b times x minus 3 all over the common denominator of x minus 3 times x plus 1. Now, up to this point, you're sitting here and you're probably looking at this and saying, what in the world are you doing with all this, trying to take this thing and do something to essentially get it back to this? We already know what that's supposed to be. Well, see, that's not what you're looking for. You're looking for your A and your B. So what we would end up with now, I would take this entire numerator, A times x plus 1 plus b times x minus 3, and I'm going to set that thing equal to 5x minus 3. All right, so let's do that. And you're going to be able to solve for a and b. So we've got 5x minus 3 equals ax plus 1 plus b times x minus 3. And when you distribute your a and you distribute your b, you're going to get ax plus a plus bx minus 3b. Now, here's the thing. Now what can we do? We've got this equation right here, or this expression equals this expression right here. How can we break that down into a relation of a's and b's that we can actually solve? Well, look only at the x terms. We know that 5x would equal, the only way we can add these or put these together is common denominator, or common terms, right? Like terms. So ax plus bx has to equal 5x. Well, what does that translate down to? That translates into a plus b must equal 5. All right, and then we can do the exact same thing with the non-x terms. So we know that negative 3 would have to equal a minus 3b. Well, if we know a minus 3b is equal to negative 3, and a plus b is 5, well, notice what we have right here. We have a system of equations right there that we can solve for a and b. So let's go ahead and do that. So, well, we could go ahead and subtract the second one. So let's go ahead and subtract this entire second equation. So we get a minus a, which gives us 0a. And we have b minus a negative 3b, so that's going to be 4b. Minus a negative, same thing as adding 3b. And then 5 minus a negative 3, same thing as adding again, so we end up with 8. Well, that means that b equals 2. Once we know that b equals 2, we can plug that into either one of these to find out what a would be. So that means that a, if I use the top equation, a plus 2 equals 5. So we would subtract 2 from both sides, and a is going to equal 3. So there is your a and your b. Now, what in the world do I want with my a and my b? Well, guess what? Where did they originally come from? They originally came from right here. So instead of the setup over here like I've got, I can actually write this as my decomposed partial fractions. So we found that a was 3 and b was 2. So 3 over x minus 3 plus 2 over x plus 1. So there is your decomposed fraction. Now, the whole purpose with this, remember, was to find the integral. Well, that makes things even easier now, because we can go right here and do the integral with respect to x and the integral with respect to x. And we end up with, we can bring the 3 and the 2 out front. And what is the derivative of 1 over x minus 3? Well, that's just the natural log of the absolute value of x minus 3. And bring the 2 out front here, and that's going to be the natural log of the absolute value of x plus 1. and then don't forget your plus c. So that's what we found. We could break it down into parts and then take the integral of each individual fraction that are much easier to deal with, and then we can get our answers here. All right, now there is a shortcut for this, and it's called the Heaviside Method. Now it only applies if the denominator will factor, which is the, well, I mean, it's got to be able to factor to do any of these, but we can only do this is if we have, if this is a quadratic and we have two linear factors on the bottom. So we're going to break it down just like this, the same exact way we did before. We're going to go that one step further and multiply by the common denominator. So we get this thing right here. Now what you're going to do now is you're going to choose x. You're just going to let x be equal to some number. Now you're going to choose the number very specifically though. You're going to choose your x so that this equals 0. You're going to solve it, and that's going to help you find what b is. And then you're going to let this one equal 0, whatever x value would make x minus 3 equal 0. And then you can go back and solve for a. So let's do that. So let's do the first one. So we're going to set this thing equal to 0, which means that we're going to let x equal -1. Now if x equals -1, that means that everywhere I have an x, I'm going to put a -1 in. So we have 5 times -1 minus 3 equals a times -1 plus 1. Well, of course, that's 0, so this whole term goes away. Now you see one of the benefits. And then plus b times -1 minus 3. Well, -1 minus 3 is -4, so we get -4b is equal to -5 minus 3, which gives me -8. Divide both sides by -4, and b is going to equal +2. Well, if you remember, that's the same thing we had for over the top of x plus 1 then as well, in the last case. All right, so if we wanted to go and find what b is, what a is, we're just going to let x equal 3. And when we plug everything in, 5 times 3 minus 3 is equal to a, 3 plus 1, and then plus b times 3 minus 3. Well, of course, that's 0, which means this whole term goes away, because 0 times b is just 0. So now we can simplify down. We're going to have 15 minus 3, which gives me 12, and a times 3 plus 1 gives me 4a. Divide both sides by 4, and a equals 3. So you'll see we get the exact same answer we had before. We have 3 over x minus 3 plus 2 over x plus 1. All right, now the good news is that the AP exam only requires non-repeating linear factors. And what that means is what we were dealing with just a second ago. Going back here, the factors in the denominator here are both linear. Non-repeating means they're not the same thing. So if we had x minus 3 and x minus 3 when this factored, that would be a repeating linear factor. So For the AP exam, you only have to deal with non-repeating linear factors. The more complicated methods of partial fractions are good to know, and you might or will probably see them in college, but they will not be on the AP exam or on my exam. But I do want you to have seen this before. Now, you don't have to copy all this down. I do want you to copy down, though, how you set it up. So, for instance, this is going to be a repeating linear factor. X plus 2 occurs 2 times. So you have basically x plus 2 times x plus 2. So the way you're going to set this up is you're going to start off with a over x plus 2 plus b over x plus 2 quantity squared. Now, this would be true no matter how far up you went. Let's say, for instance, that instead of 2, this was 4. So what would continue to happen would be this. You would add a c over x plus 2 to the third power and a d over x plus 2 to the fourth power. You would go adding them up with adding one power to the bottom until you got to the power that you were actually trying to reach, or the power that is on the bottom. So that's how you would work. So then when you come back and you would actually end up solving this, this a right here is going to have to be multiplied by x plus 2 to the third power. Remember, you're getting a common denominator. And this b would have to be multiplied top and bottom by x plus 2 quantity squared. And the c would be multiplied top and bottom by x plus 2. And the d on the good side would not have to be multiplied by anything because it already has its common denominator. And you're going to see that here. If we solve this one, and I'm going to show you the solution. Remember, just write down the setup. You don't have to write the solution unless you just want to. But you may see these in college. So we only have to multiply the a over x plus 2 by x plus 2 over x plus 2. And that's where we get the a times x plus 2 plus b, because we don't have to multiply the b over x plus 2 squared anything, because it already has that common denominator we're looking for. So now this is going to make things really, really easy to solve, because notice we have no constant, we have no x value with b. So when we distribute the x plus 2 to the a, we're going to have ax plus 2a plus b. Hopefully you can see this already. That means that a has to be 6. And if a has to be 6, and we know that 2a plus b equals 7, then we can solve for b really, really easy. So while we don't have to know how to solve these for the AP exam, we actually end up finding out that this is actually kind of easy. So then 6x plus 7 over x plus 2 quantity squared breaks down into 6 over x plus 2 minus 5 over x plus 2 quantity squared. And those are still two things that are much more easy to integrate than this thing here. Remember, for this integral right here, you would treat it as x plus 2 to the negative 2 power. This one would be a natural law. All right, now with this one, the thing you need to notice, and that should set your spidey sense off, the power on top, the greatest degree on top, is larger than the greatest degree on bottom. The first thing you need to do is divide. If the top is a greater degree than the bottom, the first thing you do is divide. Because that is actually a way of reducing the problem. Because remember, all this fraction is a division problem. So when we do this, we're going to end up with 2x. And then a fractional remainder. So we end up with 2x plus 5x minus 3 over x squared minus 2x minus 3. Now we've already done this. Then you can do the partial fraction decomposition on this and add that in. So the 2x, do the partial fraction decomposition on this part, and then you can integrate each individual part. What's the antiderivative of 2x? It'll be x squared. What's the antiderivative of this? It'll be 3 times the natural log of the absolute value of x minus 3. What about the antiderivative of this? 2 times the natural log of the absolute value of x plus 1. So that's how that would be done if this thing was an integral. So if the degree on top is greater than the degree on bottom, you want to divide first. That's where we get the 2x. Now, that one you may actually see on the AP exam because you're not using nonlinear factors there. You're not using repeating factors. You just have to do something first. Now, this one is challenging. Once again, don't write this down except for the setup because this is a nightmare of a problem. I'll show you the solution, but it's not something that you would ever have to do. And I'm going to go out on a limb and say if they ask you to do this in college, it's going to be a big bonus, or they're going to let you have a calculator for it because there's a lot of ways that you can do this and they're all long. So a calculator would definitely be helpful. So here we have an irreducible quadratic factor, which means it's a quadratic degree of greater than 1, actually degree of 2 for a quadratic, and it's not factorable. So you can't break that thing down anymore. And then we have a repeating linear factor over here. So when we set this up with an irreducible quadratic factor, it's a little bit different than when you can break it down to a linear. You actually have to have on the top 1 degree less than what you have on the bottom. So when we have this irreducible quadratic, we actually have to have a linear expression on top. That's where the ax plus b comes from. And then and only then can we deal with this repeating root over here. And that's where the c over x minus 1 and the d over x minus 1 quantity squared comes from. So if this thing is non-reducible, which we know it's not, this is a quadratic or a degree 2. On top, we're going to have to do a degree 1 polynomial, which is a linear. So let's say, for instance, that I had x cubed plus x minus 4. And let's say that's not reducible. Well, if that's one of my factors of the starting problem, then I'm going to have an ax squared plus bx plus c, and I'm going to have to solve for all those. Now, you're never going to see one of those, but I just want you to know that your top polynomial has to be 1 degree less than what's on the bottom. Since this is a squared, we had to have the ax plus b. We had to have a linear up there. All right, so let's look at this solution, but like I said, don't write this solution down because it is nasty. So just dealing with the top, we're going to have to multiply this thing by this thing. That's where that comes from. We're going to have to multiply the c by another x minus 1 and the x squared plus 1. That's what we get here. And the d is going to have to be multiplied by x squared plus 1. So then when we multiply, FOIL, expand, all that stuff, we're going to get more and more and more terms. And when we get all these terms, then we can actually get our system. And we know we've got an x cubed here and an x cubed here. So we know ax cubed plus cx cubed has to equal 0. So a plus c has to equal 0. Negative 2ax squared plus bx squared minus cx squared plus dx squared, also, since there's no x squared term over here, has to equal 0. And you would keep going all the way through and get those equations. So ax minus 2bx plus cx is equal to negative 2x. and then you would do your constant, of course. So there are 4 equations and 4 unknowns. The easiest way to do that is with a matrix and then solve that system, or use a calculator and let it do reduced row echelon so that it would actually find the solution for you. Like I said, don't worry about doing any of this, writing this all down, blah, 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 blah. So in reduced row echelon form, you end up with A being 2, B being 1, C being -2, and D being 1. So that whole thing there, we would just go back and plug those numbers in to all those places, and we end up with -2x minus plus 4 over x squared plus 1 times x minus 2 quantity squared. Simplifies down in expanded form. 2x plus 1 over x squared plus 1 minus 2 over x minus 1 plus 1 over x minus 1 quantity squared. Like I said, that's not something you're going to have to do in this class, but you may have to do it in college.